The ultraviolet catastrophe. By the end of the 19th century, the classical physics of Newtonian mechanics and James Clerk Maxwell's laws of electromagnetic radiation appeared close to explaining everything. One of the problems that remained was that of the radiation emitted by a black body. A black body is a theoretical ideal that will absorb all wavelengths of electromagnetic radiation falling on it, and should also emit all wavelengths of electromagnetic radiation, though the minimum wavelength or maximum frequency would be limited by the temperature, higher temperature bodies giving off smaller wavelength radiation. When a blacksmith is heating a piece of iron, for instance, it will initially glow dull red, then bright red, through oranges, yellows, and towards white as it gets hotter and emits more energy at shorter wavelength, higher frequencies. The theory at the time was that the frequencies that could be emitted by a black body were those for which a wave would fit into the cavity of the body with zero electric field, a node, at the wall. So, for example, this wave has a node at this wall and a node at this wall. We could have the wave going up like this, starting from the same point and having a node at each wall, or with half the wave it could be orientated like this, with nodes at either wall. These are three modes possible for this particular wavelength, starting at this point in this box. At higher frequencies, with a shorter wavelength, more modes of vibration for a particular black body are possible. As all possible modes should have been equally probable, the smallest wavelengths should have had an infinite number of modes, and so infinite amount of power should have been emitted at short or ultraviolet wavelengths. This is the ultraviolet catastrophe. If we plot a graph of intensity against wavelength, theory suggested we should have got something like this. This is the theoretical curve, with low intensity at the longer wavelengths, but as we get to the shorter wavelengths, with more modes of vibration possible, we were tending towards an infinite amount of intensity. If we look now at the actual curve found in reality, the experimental curve, it goes something like this, peaking at shorter wavelengths, but then falling off again as we get to even shorter wavelengths. So theory did not match experiment. Max Planck suggested a way around the problem. If the oscillators could only have integer, or whole number, multiples of a fixed amount, which was called a quanta of energy, the energy of the irradiation depends on the frequency, and so only oscillators with a high energy can emit high frequency radiation. But fewer oscillators would have a high energy, and so there would be a lower probability of high frequency radiation being emitted. The energy of the radiation, he said, was given by NHF, where N is an integer, say 1, 2, 3, etc. H is what is called Planck's constant, and F is the frequency of the radiation. So you could have 1 HF, 2 HF, you couldn't have 2.73 HF. Only certain multiples of energy, or certain quanta of energy, were possible. We don't notice this quantization of energy in everyday life because Planck's constant is extremely small, at 6.63 times 10 to the minus 34 joule seconds. This means that the jumps in energy from 1 allowed level to the next are far too small to notice in everyday life. Planck's theory was not at the time backed up by any experimental evidence, and so was not widely accepted. It did, however, mark the start of quantum theory and the end of classical physics. It was left to Einstein with his... no, that's rubbish.